Sometimes we miss incredible things right under our noses. Long before lions, a different sort of carnivorous mammal dominated the ecosystems of Africa, Eurasia, and North America, the Hyaenodonts. And this one, Simbakubwa, is a giant example of that now extinct group of ancient predators. But more than that, the discovery of Simbakubwa is a good example of a relatively common phenomenon in the evolutionary sciences: the discovery of something amazing and unknown, sitting forgotten in a museum drawer. Back in 2013, an American paleontologist called Matt Bortz was visiting the collections of the Nairobi National Museum in Kenya. By chance, he happened to open a collections drawer and found something completely unexpected: the fossilized jawbone of an extinct and giant carnivore. To give you a sense of scale, here it is pictured from a few different angles, with the jaw of a male lion here at the bottom for comparison. That scale bar is 5 cm long, making the preserved portion of the jawbone about 40 cm in length, nearly half a metre. But 2013 wasn't the start for that fossil jawbone. It had originally been excavated at the Meswa Bridge locality in western Kenya, sometime between 1978 and 1981, and from there it went to the National Museum in Nairobi, where the curators catalogued it and shelved it, and then it was seemingly forgotten and left unstudied for decades, until 2013. Bortz collaborated with another paleontologist called Nancy Stevens, and together they wrote and published a paper together in 2019, describing the remains as a new species, Simbakubwa kutoka Africa. That comes from the Swahili meaning big lion and from Africa. Yes, if you didn't already know, Simba's name literally means lion. But don't let the name fool you. Simbakubwa isn't a lion. It is a member of a now extinct group of mammalian carnivores called Hyaenodonts. And don't let that name fool you either. These are not particularly close relatives of hyenas either, even though they do all belong to the same carnivorous lineage of mammals. More on that later on. The jawbone was found preserved alongside a fragment of top jaw, both of them with some teeth still attached, as well as several isolated teeth. This was enough to start making some inferences and gleaning deeper insights about the life and biology of this extinct giant predator. For example, it belongs to a subgroup of the Hyaenodonts called Hyaenolurinae. These Hyaenolurinae contain some of the biggest Hyaenodonts. The biggest I could find reference to, Megistotherium, possibly weighed somewhere between 1,800 and 3,000 kilograms, although estimates do vary and those were the biggest ones. Simbakubwa seems to fit in with this trend of large size. Remember that we saw earlier how much bigger its jaw was than a lion's. Bortz and Stevens used what is called a regression analysis to try and deduce an estimate for the weight of Simbakubwa based on the preserved jawbone and tooth specimens. This is based on the correlation between various features of a creature's anatomy and their overall size. For example, how people who are taller also tend to have bigger feet, so if you knew someone's shoe size, you could, at least theoretically, get an estimate of their height. For mammal carnivores, this is usually done using the length of the first lower molar tooth, often noted as M1 with a lowercase m in paleontological literature, and often referred to as the carnassial in the context of carnivores. And note that that's length end to end along the jawbone, not the height away from the bone. A quirk of Hyaenodonts is that all of their molars count as carnassials, as they all form so-called carnassial blades, rather than just the first one, like in other carnivores. Not all of these teeth are preserved in the jawbone of Simbakubwa, although the holes where they fit are still visible and can be measured to act as a proxy. There were also some isolated carnassial molars attributed to Simbakubwa in the collections at the National Museum, and so the researchers were able to get an average length measurement across all of them. Using some straight line equations intended to reverse engineer body masses from carnassial molar lengths, they got mass estimates of between around 1,308 kilograms and just over 1,550 kilograms, both of which are substantially heavier than the polar bear, the largest land carnivore alive today. However, because nothing can ever be simple, they also got a third estimate from a different equation, this time of only 280 kilograms. And that's still big, bigger than the vast majority of modern lions, but it's only about 1/5 of the heavier estimates. That difference comes from how the different equations they used were optimized, things like which specific subgroup of carnivores they were intended for, and exactly which measurements you use in them. These methods only work because the size and shape of teeth tends to vary in accordance with overall body size. However, the exact correlation may vary between groups. And that's where the differences in estimates come from between different equations. In this case, the heavier estimates came from more hyaenodont-specific parameters, and the smaller one came from an equation optimized for use on megacarnivores in general. It's hard to say with any real certainty which of those estimates is more likely to be accurate, but we can be reasonably sure that Simbakubwa was big, somewhere between the size of a really big lion all the way through to bigger than a polar bear. And as we mentioned earlier, large sizes like that aren't that unusual among the hyaenodonts. And now might be a good time to explore that extinct group a bit more. Like I said earlier, don't let the name fool you. Hyaenodonts are not that closely related to modern hyenas. In fact, they were the dominant mammalian predators before the origins of the other more modern mammalian predator groups, things like hyenas and bears, as well as cats and dogs. Their fossil record goes back a long way to the Paleocene epoch, the period of around 10 million years just after the KPG mass extinction, that, among other things, wiped out the dinosaurs around 66 million years ago, and the origin of the group is probably around about the time of this mass extinction event. Simbakubwa is more recent than that though. It was found in rocks from the Miocene epoch, and probably lived around 22 or 23 million years ago. That makes it the oldest known of the giant hyaenolurines, but also one of the most recent among hyaenodonts as a whole, who had mostly gone extinct earlier than that during the Oligocene epoch. For context, the Ursidae, that's the family containing all modern bears, is estimated to be around 21.5 million years old, as is the dog family Canidae. Meanwhile, the cat-like lineage of carnivorans, including things like the cat family itself, Felidae, as well as other related things like hyenas and mongooses, is estimated to originate around 34 million years ago. That origin is much older than Simbakubwa, but also tens of millions of years after the hyaenodonts had already started to diversify. Do bear in mind though that these are all just estimates, based either on genetic or fossil evidence, and are subject to near constant debate and change. During this time, hyaenodonts had a wide distribution all around the world, with the exceptions of South America, Australia, and Antarctica. Trying to figure out how these animals lived during that time is challenging, and relies almost entirely on inferences made from the fossil record. What we can tell for sure about Simbakubwa is that it was big, as we've already talked about in depth, but also that it was likely hypercarnivorous. We can also tell from tooth wear that some other giant hyaenodonts, and hyaenolurines specifically, could probably process bone in their diets. But Simbakubwa seemingly couldn't, at least based on the lack of tooth wear seen on the Nairobi Museum specimens. The very large hyaenodonts, like Simbakubwa and Megistotherium that we mentioned in passing earlier, could have occupied a very specialised predatory niche, being the only carnivorous mammals at the time that could have preyed on the larger herbivore prey that was starting to evolve during the Oligocene and Miocene epochs. Things like early relatives of rhinos and hippos and elephants. And this could be part of how these last hyaenodonts fell to extinction, although everything that follows is somewhat speculative. Both they and their possible prey would have been very large in size, and so likely also had long generation times, meaning that they reproduced slowly. This means that any significant disruption to climate or environment, even relatively briefly, could have had substantial impact on their populations, and left them on terminal decline towards extinction. And these sorts of changes were happening during the Oligocene epoch as the majority of hyaenodonts were going extinct. Global temperatures were cooling, ice sheets were reforming over Antarctica, and global habitats would have been shifting in response to this, altering what sort of prey they would have been able to support. And it was also around about this time that the other groups of carnivorous mammals were starting to evolve and diversify, as we mentioned earlier, and it's possible that competition from these newly evolved predators could have edged out hyaenodonts as time went by. Remember though, this is all based on somewhat speculative inferences from the fossil record, and the exact cause of the hyaenodonts' extinction is still under debate. So much of the distant past is lost to us that it becomes really hard to be absolutely sure what really happened so many millions of years ago. Now, there's one more thing that I've mostly glossed over so far. Simbakubwa was only found and studied after sitting in a museum drawer without seeing the light of day for decades. And this sort of thing actually happens quite often. Around about the same time as the Simbakubwa paper was published, a different group of researchers published a paper describing a new species of mastodon, this time after noticing that a skeleton on display in a museum in the US was distinct enough from other American mastodons to warrant a new species classification. And it can get even more extreme than that. An entire order of insects, the Mantophasmatodea, only became known to science in 2002, after specimens collected decades earlier in Namibia finally became studied, and the researchers realised that they didn't fit in with any other known group of insects. Basically, someone working in a natural history museum in the entomology collections opened a drawer and went, "What the hell is that?" And to try and put this in more context for you, order is the taxonomic rank above family. So this is like the insect equivalent of a group as significant and evolutionarily distinct as primates or bats, being unknown to science, but with specimens just sitting in a museum drawer. It might seem outlandish that this sort of thing can happen, but in reality it's really not. Museum collections are far bigger than what you see on display, often running into tens of millions of specimens in larger museums. And relatively small teams of curators and researchers can't possibly keep up with all of the newly discovered material, let alone what's already piled up over decades, if not centuries, of old collecting trips and donations from private collections. As Matt Bort said when he found Simbakubwa in that drawer in the museum in Kenya, there are tons, probably literally, of new species lurking in museum collections. And I'll leave it there, on that notion of great discovery lying right under our noses. Thank you for your time.